Everybody. In this presentation, I want to say a few things about search, explaining that it's a fundamental tool in AI, as well as formalizing a problem for search, and as well as states and state spaces. I mentioned to you that a couple of years ago, I wrote a paper with a bunch of colleagues, and we surveyed practitioners and educators about what's the sort of stuff that we should teach in an AI course. And the one item that got over 90% of the responses was search. So that should tell you that search is a fundamental tool in AI. We will see some applications, we will design and write some applications, but we'll study some of the cutting edge stuff like AlphaGo, Watson, and some others. And they all use search, natural language processing. They use search. So you can't get around doing AI without knowing something about search. Now, there are many different search methods around. Data structures, and data structures we do some search. And you shouldn't dismiss any of the search algorithms. You'll be surprised about finding what is being used in some fairly challenging and high-profile applications. So let's talk a little bit about search. The first thing we're going to do is we're going to talk about formalizing a problem for search. So in the context of search, we have a start or initial state. We have a description of what actions are available to an agent. Then we have a description of what the action does, like a transition model. We have a goal test. Sometimes it is actually a concrete goal. Here, this is what I want you to do. And then eventually we have a path cost. What's the cost of getting from the start to the goal? So the initial state with the actions and that can be performed in transition model define a state space. So the state space is typically a graph, something we will see in a moment. However, most of the time people draw them as trees because it's just easier to sort of like understand the trees and navigate them. But a path in the state space is a sequence of states connected by a sequence of actions, just to be on the safe side. So let's have a look at a state, say, from the sliding 8 puzzle, right? Here's a state. This is what it is. This one is the empty one, right? And so we know what the goal states are. Sometimes it's 1, 2, 3, 4, 5, 6, 7, 8 around the perimeter, and sometimes it's 1, 2, 3, 4, 5, 6, 7, 8, right? That's the goal state. And so we got to get from here to a specified goal state. So how are we going to do that? So here is an example of a state space. Again, a random Sudoku, sliding 8 puzzle. So 1, 2, 5, 3, 4, 0 is the empty space, 6, 7, 8. So we can move 5 down, 8 up, 4 to the right. So 4 to the right, 5 down, 8 up, right? Those are the 3 successes that we can get. So let's have a look at this one over here. Well, now we have 4 successes. 2 down, which is this one over here. 4 to the left, which is this one. 3 to the right, which is this one over here. And 7 up, which is this one over here. So those are the successor states. Now, somebody say something interesting about this state over here. It's the same as the start state, right? So if it were a graph, we would have an arrow from here to here, and then from here to here. But a lot of times we don't do that. So we have this state space, search space drawn as a tree. And so we eventually need to make sure we understand that, wait a minute, from here to here to here, it's a cycle. And we want to avoid cycles because it just means you do extra moves. You go back and forth without gaining anything in terms of a competitive way of playing the game. So I'll say more about that in the next presentation when we look at uninformed search methods. But this is it. So you got to find a path from the start state to one of the goal states. So there are different ways of doing this thing. Breadth first, depth first, and many, many others. All right, folks, that's it. I'll see you then.